Imagine you're on a roller coaster. The moment the ride starts, it suddenly jumps to full speed without adjusting for curves or inclines. No brakes, no corrections, just raw power applied. What do you think happens? Chaos, right? Well, this is quite similar to what happens when a PID controller operates in an open-loop system. A PID controller, proportional, integral, and derivative, usually works by adjusting its output based on feedback. But what if there's no feedback? That's an open-loop PID. The controller responds purely based on the input signal without knowing what actually happens in the system. Now let's assume we have a closed-loop PID controller for a process and it's operating stable, meaning set point and process variable are matching. Now let's cut the feedback to this PID controller to make it an open-loop PID controller and apply a step change in either set point or to the load input of this process. So how does this open-loop PID react? Well, let's break it down component by component. As the PID equation says, the PID output will shoot to maximum for a moment in response to when a step change is applied due to derivative control action. The derivative component says I will generate an output whenever I see there is a rate of change of error, and it will be as strong as the proportional component would have replicated in a particular time you set, I mean derivative time. Since a step change has an infinite rate of change, the derivative term creates a sharp spike in PID output initially, but then quickly settles and stops generating any output as the rate of change of step input comes to a halt now. Here, the proportional component comes to take charge. It says I will generate an output proportional to error multiplied by the gain you set. So the open-loop PID controller sets the output proportional to error multiplied by proportional gain after the derivative component settles and stops generating output. Now comes the integral component. It says I will keep adding past errors for a period of time you set. I mean integral time. So the integral component keeps accumulating error over time, causing the output to continuously increase or decrease like a ramp effect, and tries to bring the process variable to set point. But we have kept feedback open, so the PID output will keep increasing output to maximum. So an open-loop PID controller responds to a step change with an initial spike, D, a jump, P, a ramp effect, I, and however without feedback it can't self-correct, leading to instability or inefficiency. This is why most practical PID systems use closed-loop control, ensuring accurate and stable operation. Thanks for watching. If you found this breakdown helpful, don't forget to like, subscribe, and hit the bell icon for more deep dives into control systems. Got a question? Drop it in the comments below. See you next time.